started early and leave anybody behind. Two important people are here now. Just kidding, you're not late yet. Exciting volleyball game last Friday night. And they win on a, what was it, a service fault that,
Yeah.
Did you guys watch it?
which cracked me up.
No.
Because I had like so many people approach me like that was in. I'm like, no. And Danny's like, I'm only watching on film, let you know. Danny's like, I thought it was out.
I thought it was in.
It
We were like, ow! And we looked at you. I looked at you. And
Well, see, I think he was just making up for one earlier in the match, in the first game, that how do you call that in? It looked out, and he pointed in, and then came down to, it was match point or something, and they were serving, and it looked like it hit the line. I said to my wife, did that hit the line? Oh, I thought so. Win. But if they hadn't got it on that point, they'd have got
I
it.
didn't see that, so I hope you got it right. I'm like, yeah, I got it right.
oh my god, for sure.
But anyway, they were going to win anyway. It didn't come down to
Yeah, that was wrong.
That was the makeup.
Because they were in the net and they hit it. They hit the person that hit the ball hit the net first, and then your other person hit it afterwards.
That was bad.
So, all right. I guess it's almost noon. I'll go ahead and get started. You want to go ahead and,
I accidentally recorded that whole thing.
okay, that's
I
fine.
thought I turned it back off.
That's fine. I'll just have the people delete it out. Otherwise, they get a nice discussion about volleyball. Last time we did section 8.2, which was confidence intervals for proportions. So I'll start with any questions remaining on that. Anybody have any questions that they want answered on maybe the homework that's due tonight or whatever? Yep.
The one that was due on Friday, I had a question about this finding the standard error with it was number 2. If I saw it, I would know, but it was, you had to fill in the bottom. It was like 95% with a number and then like the population sample. And I couldn't figure out how to figure out the standard error with the information I had given us, because it was like a list of 8 numbers, like 1, 2, 2, 0, 5.
Oh, it sounds like it would be, well, no, I guess that could have been section 8.1. But probably what they want you to do is to compute the standard deviation of those numbers and then divide the standard deviation by the square root of the sample size.
Okay.
And that gives you the standard error. And that's the part that everybody's forgetting, that standard deviation is different than standard error. Standard error is if the population standard deviation is sigma sub x, then the standard error of x bar is sigma sub x over the square root of n. So you have to remember to divide by the square root of the sample size. Okay? And we're going to use that a lot for today because we're going to do confidence intervals for means, which we'll jump right into if nobody has any other questions about population proportions. Ready to go? All right. So section 8.3 is very similar to what we did before. We've been saying now for a couple of sections in a row that in general, a confidence interval is a point estimate plus and minus some critical value, which I'm just going to call CV, short for critical value. A critical value times a standard error. Standard error of that point estimate. Okay? So now we're going to do means problems. So we need to figure out, well, what is the point estimate? What is the standard error? Those come directly from the central limit theorem. When we're doing a means problem, we're trying to estimate the population mean. And what's the notation we use for the population mean? We got population standard deviation, I just wrote that. What's the population mean? It's just notation. What symbol do we use?
P hat?
Nope, that's a proportions problem. And I'm glad she said that right there because I wanted to say, from here on out, the rest of the semester, almost everything we do is either a means problem or it's a proportions problem. And you got to keep those two straight. And the formulas are going to get all mixed up in your head. Which one's proportions? Just always think, if it's got p's in it, what kind of problem is that? Proportions. If it's got means, or if it's a means problem, it'll be mu or x bar for sample mean. So if it's got x bars or mu's, it's a means problem. If it's got p hats and p's, that's a proportions problem. So keep those formulas straight. The big mistakes happen when you try to intermingle those formulas and things don't work out. It's kind of a joke, but unfortunately it's true. People do this. If you find you don't have all the pieces you need for the formula that you think you should be using, and you start making up numbers, well, maybe I'm supposed to put a 5 in there, then you probably got the wrong formula. You're probably doing a proportions when it's supposed to be means or vice versa. So we need to figure out this general formula. So the point estimate, if we're doing means problem, what's the point estimate of mu? Give me a hint.
You said X bar?
X bar, right? That's the point estimate. If you're trying to estimate a population mean, you do it with the sample mean. Anytime I ask what's the point estimate of this, the answer is always, it's the sample one of those. Right? So if I say, what's the point estimate of a standard deviation? Oh, that's the sample standard deviation. Got it? So that's going to be my point estimate, x bar. Plus or minus some critical value. And I'm purposely not telling you where to get that critical value just yet. We'll get there in just a second. What about the standard error of x bar? It's right here. Standard error of x bar is sigma x over the square root of n. That looks just dandy, doesn't it? See any problems with doing that in practice, though? Where are you going to get sigma x? What is sigma x? Population standard deviation. Are you ever going to know the standard deviation of the population? Particularly, are you ever going to know that without knowing this, the mean of the population? Because that's why we're doing this, right? We're trying to estimate the mean of the population. There's never going to be a case where you, I'll never say never, almost never going to be a case in practice where you would happen to know the population standard deviation but not know its mean. There are some cases, like for instance, IQ tests. Those are set up purposely to have a standard deviation of 15. So you may have a population, I want to know the population of females, how they do on IQ tests. Well, you can assume, well, the population standard deviation is going to be 15. I just don't know what the mean for females would be compared to the mean for males or whatever. Okay. So, but those are kind of contrived examples. Almost never will you know this value. Right? Well, now that I'm turning you into statisticians, if you don't know the value of something, what do? You estimate it. So what's the estimate of sigma sub x? Sx, the sample one of those, right? So actually I'm going to leave that sigma there. I'm going to put an x through it and then put in Sx. And down here I'll say Sx because sigma x is unknown. Okay? Now the problem with this is, and that's why I've been leaving this CV unspecified at this point. When we had a proportions problem, we used a z there, right? Z critical value. Well, it's not going to be z with a means problem because of this. What happens is, in a proportions problem, we didn't know p, so we put in p hat, and the standard error was p hat over 1 minus p hat over n. And then we had p hat also as the point estimate, and then we had a z critical value up front. There was our confidence interval. Well, when we put p hat in here, we did not add a new random variable into the mix. It's the same random variable that we use as our point estimate. But look what happens here. It's a different random variable than the one we're using as our point estimate. So we added more variability. We added more randomness, another random variable. When you do that, it's no longer a normal distribution. It's what we call a t-distribution. So the critical value becomes a t critical value, not z. Okay? So I'll talk a little bit later on what exactly that t is. I don't have time. There's a lot to cover today, so I'm not going to cover where historically that t distribution came from, but it's an interesting little sidebar, and it is in the book. They've got a little box that talks about a guy named William Gossett who discovered this. The thing that college students like is he worked for the Guinness Brewing Company. So anyway, it's going to be a t critical value, not a z critical value. And I'll show you in a minute where you're going to get those critical values. But to motivate all this, now let's go back to our pulse data and our distribution. This was the distribution of pulses for all 385 values that were turned in. And I'm just going to remind you, actually I can page down to here. And here we're going to treat these 385 observations as if they're the whole population. Right? And we're going to sample from that population. So my mu, in this case, we get to play the role of God. We get to see, we get to know what the population is. In practice, you'll never know these values. And that's why you're trying to estimate them. But for now, we're going to pretend like we know it. And it's 71.667 for the mean. And the standard deviation is 10.315. So across the top line, 71.667, and standard deviation 10.315. That's the population parameters that we're going to pretend now we don't know, and we're going to estimate. Okay? So I showed this picture. I jumped past it. That is, you remember what this is? I showed it on the day we did section 8.1. What's the difference in this histogram and that one? Whoops. Oh, I hit the home button, not the page down button. There we go. What's the difference?
One of them shows mean, and the other shows all values.
This is all values, 385. So this is the data distribution, or in this case we're pretending that's the population. So that's the population distribution. There's the, what do we call this distribution? Sampling distribution, right? Now, once you look at this sampling distribution, do you see anything odd with it? What?
Narrower.
It is narrower, right? Because of the thing I erased. S, or sigma, over the square root of n makes the standard error smaller, right? So it gets skinnier. What about this observation? Does that look odd? This is an outlier, right? This is a sample with a mean of 46. The normal distribution that approximates this is the blue curve, and you can see that by the time you get to there, it's down to nothing. And it's saying there shouldn't be any out past this. But there is. There's one that's out past that, right? So I went exploring to see where that point came from. And that came from Morgan Rainey. Morgan Rainey. And I'll show the numbers in a second. So just keep in mind, actually I want to jump out of this for now, and I want to go to this and show confidence intervals. Now that you can't read, so let me make it bigger. These are the same summary statistics I just had in that PowerPoint presentation, same numbers, and then here are the numbers for the 77 samples that you guys sent in, right? Same exact mean. I showed these the other day. Same exact mean, and in yellow is 6.568, which was the standard deviation of the 77 sample means, right? Now, do you remember we then computed this 10.315 over the square root of 5 as the standard error of x bar. You remember what that number was? You're supposed to memorize all the numbers that we ever show in the class. I actually remember it's 4.61. And remember we discussed a little bit that this number is too big. The theory says it ought to be 4.61, but it's a little bit too big. Right? Part of the reason it's a little bit too big is because of Morgan Rainey's data point, with that 46 being way out there. What happens if you get an outlier? What happens to the standard deviation? It goes up, right? It's not resistant to outliers. So that's part of the reason, but there's a lot more reasons of why it's like that than just her. I can't put the blame all on her. We're going to share equally in the blame here. So, before we continue that discussion, let's look at some actual data here. It might help if I bold this. No, it didn't help at all, did it? Can you see that any better? You can see that, right? She can't. Her eyes are closed. But now can you see it?
Yes.
Oh, that helps. Huh? Okay, now this is section B. That's my first class. And what you're seeing here is for each person that sent me data, here's their x bar. So that's the mean of their 5 observations. Here's their standard deviation. And then lower and upper. Guess what those are? No. That's a good guess. They're not quartile ranges. Think confidence interval. That's the lower and upper bound of the confidence interval. Remember, the confidence interval is point estimate plus or minus margin of error. So that's subtract the margin of error, you get the lower one. Add the margin of error, you get the upper. Okay? Now this first one here, actually let me go down to your class. This is section B. Let's go down to your class, which is section C. And we'll just, we'll pick on whoever's top here. AMA, who's that? Who's AMA? Nobody that's here today? Who's AMC? Not here? These people probably all drop. I know this one. 4 initials. That's Delaney, right? Delaney gave us a sample with a mean of 65. So I'm going to come, where can I go? I guess right here. X bar is 65. Right? Standard deviation from Delaney was 6.083. So SX is 6.083. And then our confidence interval then goes from 57.45 to 72.55. Then I have a column that I say is cover. And it has a Y in it. That Y is for yes. And by cover, I really wish I had used the word capture. I like that word better. Does the confidence interval contain the population mean? That's what that yes is saying. So 71.667 is in Delaney's interval. So she gets a Y. right? So let's go down. Here's one with no y. That interval, that came from J-E-K. Who's J-E-K? Okay. That's Jessica Kopp. And her mean was 66.0. Right? Not too far from Delaney's. Why did she miss and Delaney got it? In fact, her interval is, the entire interval goes 62 to about 70, 69.9. So the whole interval is below the mean. But her standard, I don't want to say that yet. Her interval, her point estimate is actually higher than Delaney's, 66 instead of 65. But Delaney's captured the true value. In other words, she got it right, you got it wrong. Remember what 95% confidence interval means? Or what the interpretation is? I'm 95% confident the true value's in there. Well, Jessica's is not in there. How come she missed? What makes you miss? Standard error. And her standard error is too
small.
yeah, it's either too big or too small. If it were too big, what would happen to the interval? It'd get wider and wider and wider, and then you're going to capture, right? So it's too small. Well, look at her standard deviation, 3.16. Remember, the standard deviation in the population was 10.3. So she way underestimated the standard deviation. Okay? So her interval's too small. But that's going to happen from time to time. You got a question?
Yeah, I was just looking at mine up there, JLR, and mine was 70, but my standard deviation is only like 2.5.
Good. Your standard
Mine's-
deviation is even lower than hers, right? You're really bad. Just kidding. But yours captured. How come? Because your mean was closer to the true mean, right? So your interval's even shorter. It's just shifted over, right? But you got to realize, hey, these are 95% confidence intervals, right? We know not all of them are going to contain the true value. In fact, what percentage of them should contain the true value? 95%. That's what we mean by 95% confidence. 95% of all the samples drawn should contain the true population mean. 5% should miss. You just hope that you're not one of the 5%, like Jessica. Got it?
Yep.
So what I've got here in this last column is cumulative, the coverage percentage. So it's saying by the time I get this many Y's, my percent out of 77 keeps going up. Right? So, and then when I hit Jessica's, it doesn't increment. It goes from 44.2 to 44.2 because that one didn't add another Y into the mix. But by the time I get to the bottom of all of the sections, including my online section, what should that number be? 95%. Because these are 95% confidence intervals. You want me to prove it? Okay, there's the section and there's the end. 77 of them. And look at the coverage probability. Oh, crap. It's supposed to be 95%. It's 79%. Oh, I know what's wrong. You guys didn't do 95% intervals. You did 79% intervals. You just lied. Said they were 95%. Wait, I computed them, not you. So I lied. You think that's what's going on? Yeah, you're lying. Why does this not work? Now here's true confessions of a statistics professor. The first time I ever had a class do these intervals and give me pulses on 5 people was for this lecture. So that my thought was, ooh, then I can show repeated sampling, and if you compute a confidence interval from every sample, 95% of them contain the true value. And when I did it, that semester it was even worse than you guys. It was 71%. And my thought was, they lied to me in graduate school. They said this stuff works. And it didn't. It didn't work. And then I remembered, oh, wait a minute. There were certain assumptions that had to be met before you could trust the statistical inference. And the book lists these assumptions. So here we go. Let me do them under here for now. For means problems, there's two assumptions that have to be met. The first assumption is data come from a random sample. The second one is data either come from a normal distribution or n is greater than or equal to 30. Remember the central limit theorem? The central limit theorem said that the distribution of x bar will be approximately normal with this mean and this standard error. Where did I write all that? With, I guess I erased it. But with this standard error, as long as the sample size is at least 30. So that's where this n greater than or equal to 30. If you have data that comes from a normal distribution to start off with, like pulses, then you don't have to worry about n equal 30. You're going to be normal right off the bat. But if you come from a really skewed distribution, like our distribution of ages, then you shouldn't be using samples of size 5 to do inference from. You need to get samples of at least 30 before you trust that the central limit theorem has kicked in and made this approximately normal. But for our data, we don't have to worry about that because pulses are pretty normally distributed. So sample of size 5, we meet this restriction. Data comes from a normal distribution. So which assumption do we not meet?
Random sample.
Random sample. And we've talked about this already in here. How many of you used random sampling to get your 5 people? Nobody. What kind of sampling did you use? Convenience sampling. So what does convenience sampling do to screw this up? It very clearly doesn't work. 79% when we should have had 95%. Why does convenience sampling cause that problem?
We picked certain age groups.
Okay, we picked certain age groups, so what might that do? Think about the two things that could make your interval miss. Because what's happened is our intervals miss too often. They should have hit or captured 95% of the time. They only captured 79% of the time. So we're off a lot there.
And it distort our mean.
Okay, it could distort the mean. So bias, right? Biased mean. Okay? Now, why would convenience sampling potentially bias the mean? And what were you thinking, Kristen, when you... It's not Kristen, it's Crystal.
Yeah.
Sorry.
Okay. I don't know where I was going with it.
Well, no, you're on the right track. I don't want to scare you off. But
Because ages, if you pick similar ages, they're gonna have similar, or people that are around you are gonna have similar resting heart rates as you.
Okay.
So it's not gonna have the wide range of values as a random sample.
if you pick mostly young people, like most of you did, young people tend to be more active, more athletic, and have pulse rates that are lower. So that's biased towards the population mean, right? But now remember, our population, we're sort of artificially saying, well, our population is the 385 that you sent me. So it kind of takes that into account there. And we still missed. We still only hit 79%. Right? What's the other thing that can cause a confidence interval to miss? The mean is biased, so it moves it off away from the population mean. That's one thing. What's the other thing? The standard error. If the standard error is too small, your interval is going to miss, right? Because no matter where you center your interval, if you shrink it down small enough, pretty soon you miss 71.677, right? So we had too many people that had really small standard deviations, like Jory, right? Standard deviation was 2 something. I got a page back up to see what it was. She's right on this line. Her standard deviation was 2.4. Now some people got a standard deviation that was even bigger than the population standard deviation, so it didn't affect everybody. KMT, who's KMT? They're not here? Okay. So some of them are not too small, but on average, more of them are too small than you would expect with random sampling. Now let's think about why that is. Why would using convenience samples tend to underestimate standard deviation? Or in more layman's terms, why would convenience sampling tend to underestimate the total variability in the population?
Because working variables will make the values similar, so there's not as much difference. Like I pick my family all has heart problems, my dad is a pacemaker, so his pulse is artificially low, and so, you know, the whole family has a lower pulse than
Okay, so you got both problems going on in your sample, right? You have a biased mean because of your dad, right? And then you got standard deviations that are too close together because you used all people that were genetically related. So they're not going to have as much variability within those 5 people as you would expect from 5 randomly selected people from the whole population. Right? Now let's come back to Morgan's sample, the one that was at 46. Do we see it on here? Yeah, right there. Let me pull the screen down. There's Morgan's sample, mean of 46, standard deviation of 2.9. Did she miss? Yeah. Look what her confidence interval, 42 to 49. She's saying she's 95% confident that the population resting pulse is less than 49. And we know that's not right. Right? Now, your sample. The thing I know about Morgan is she's on the tennis team. Right? She's an athlete. Athletes tend to have pulses that are low. Right? Did you use other athletes in your sample? All of them were on the tennis team. So guess what? She caused both problems. She biased the mean low, and she biased the standard deviation low, because she picked people who all are very similar in heart rate because they're all working out together, right? And they're exercising and all those things. So don't trust the statistical inference if you didn't use random samples. Now I do a lot of statistical consulting, and I got really smart people, PhDs and MDs and people like that I consult with that don't understand this problem. And there's not much of a way to make them understand it other than show them you guys' data and go, look, you know, it causes problems. They think, well, no, it wasn't a random sample, but, you know, it's representative. Well, if I asked you if your 5 people were representative, you'd probably say yeah. But until you see it all together in a sampling distribution, you don't realize, well, I guess not. Right? If you don't use random sampling, you can't trust the statistical inference. So here's the take-home message. These assumptions are rules that have to be met. And if you don't follow the rules, don't use the tools. You like that? I made that up. If you don't follow the rules, don't use the tools. So every homework problem, every test problem is going to say, check the assumptions that are required, and then produce a confidence interval. And most people will forget all about the assumptions because that's just nuisance. I want to get to the fun stuff of computing numbers, right? But you got to check the assumptions. most of the problems that will work in the textbook will meet the assumptions, and sometimes you can't tell. And I want you to write that. Right? On a test, I may forget to say the data comes from a random sample. So you say, well, assumption number one, it doesn't say whether it's random or not. I have no idea, so what follows may be suspect. But go ahead and do the rest just in case I just forgot it, right? But I may blatantly say, these data were collected using voluntary response samples, and here's the confidence interval. And your answer should be, this confidence interval cannot be trusted because you didn't use random sample. Okay? So, my thought when I looked at this data was that you guys can't draw random samples to save the world. So what I did was I had the computer draw random samples. Essentially what I had the computer do was take the 385 observations and randomly divide them into groups of 5. So I got 77 random groups of 5 out of that population. Okay? When I do that, I get the same kind of printout here, and I have the same thing. Cover, yes or no. So we got yeses, and there's a no, right? A blank. That one missed. The upper bound was 70.25. When I get down to the bottom, to the 77th observation, there's the coverage probability. 94.8%. It does work. So this method of producing confidence intervals works the way it's supposed to, as long as you use random sampling and you meet the assumptions. So 95% of them contained the true population mean, and 5% of them missed. Now, don't get picky on me. Why is it not exactly 95.0? Because I have 77. And if you take 73 divided by 77, you get that number. If you take 74 divided by 77, you get 76 point, or 96 point something. So 95.0 isn't possible with a relatively small number of samples. The central limit theorem and the theory behind all this assumes the infinite number of possible samples you could have drawn. Now, one thing that I think is worth pointing out at this point is this. Of the random samples of 77, same mean, but the standard deviation between them is 4.578. What did we say the theory said it should be? 4.61. Hey, we got real close, right? We got rid of all the bias, all the problems with convenience sampling, and that works too, right? It isn't exactly 4.61 because, again, we're only looking at 77 out of all the possible samples that we could have drawn, but we got 4.58 if you round to 2 places, so really close, really well. Okay? Which brings up a point. I sometimes get a question here, well, how do I do this in practice? I can see that if I have 77 samples, I could estimate the standard error and the distribution and all that, but I'm only going to have one sample. I only get to look at one sample. How do I do this? Well, the theory tells us what the standard error should be, sigma over square root of n, even if I don't have 77 or 100 or 1,000 different samples to look at. It works. So 4.61 is what it ought to be. The theory matches with what you see in practice. So you only have to look at one. You can still compute the confidence. Okay, now let's go back up into the data set, and we'll just pick random sample number 1, which is right there. If I highlight it, can you still read the words?
Yes.
Okay, and we're going to do it using this rule by hand, and then we're going to do it using our calculator, because your calculator has these confidence intervals built automatically into it. Okay? Which reminds me that I have to talk about the t-distribution and where you get that critical value before we can do this by hand. So, the t distribution, remember when we had a z distribution, if I wanted 95% confidence, what number did we use?
1.6.
Oh, yeah.
1.96 for 95% interval, right? It was 1.96. But I said a t distribution has to incorporate more variability, which means it has it's wider distribution, right? More spread, more variability. So you're going to have to go further out to get 95%. So the critical value will be bigger than 1.96. Now the t critical value, I guess I'm done with all this. The t critical value depends on degrees of freedom. And the degrees of freedom are n minus 1. Now, real early in the semester, I talked about degrees of freedom when we talked about the formula for Sx, the sample standard deviation. And remember, it had a bunch of stuff. This is not what I'm talking about, but it had an n minus 1 on the bottom of the fraction, and that is the degrees of freedom. So the degrees of freedom for the t critical value come from the divisor in the sample standard deviation, because that's what's being used in this, right? So you don't need to really understand that very well, just to realize that my degrees of freedom are one less than the sample size. Okay? So let me pull up the t table, which you can find in the back of your book. If you turn to page A3 in the appendix of the book, you'll see this table. And the way you read it, on the leftmost column it says df for degrees of freedom. You go down to whatever your sample size is, subtract 1, and you go down to that level. So for this interval that we're doing, we have a sample of size 5. So what's our degrees of freedom? 4. So we're going to go down to 4 degrees of freedom, and then you go over to whatever confidence level you want. We want 95% confidence, so the number sitting right there is 2.776.
What page is this on?
It's page A-3. They stop numbering them with numbers when you get to the appendices, so it's just A-3. Okay? Now, if you have a TI-84, this table's built into your calculator. If you have a TI-83, sorry, you need the one in the book. So on the next test, I will have copies of this table available that you can use to look up t-critical values. You don't have to make room on your cheat sheet for that. If you have a TI-84, it's pretty easy to get out of there. So let me go ahead and show that right now. You're going to push the stat button, and then you're going to go, I'm sorry, not stat button. Second function distr, which is second function vars, and then you're going to pick the t, or it's inverse t, inv right? Is that, are you looking at yours? Okay, inv t, and I can't remember if he uses a capital T or a little t, but capital. So, and then it has parentheses, and what you enter into that, this is just like the inverse norm function. You enter the area to the left of the critical value you want. So if you want 95% in between, you have to add back in half of the leftover percent. Remember doing that? So instead of 0.95, you're going to enter 0.975 or 0.025, which will give you a negative one, and you just ignore the negative. That's kind of how we did it for the normal. The t distribution is like the standard normal distribution. It's always centered at 0, so you don't have to enter the mean and standard deviation. You just enter the degrees of freedom. So you would enter, in this case, 4, and that's degrees of freedom. So this is area to the left and degrees of freedom. When you do that, you should get 2.776. I'm not seeing anybody with an 84 over here. What'd you get? Yeah,
I haven't done it yet.
we'll do it. Joy, what'd you get?
I haven't done it either, I was writing it down.
Okay. Did you get it? I just want confirmation.
2.776.
Okay. I wanted to make sure I was remembering the numbers and how you enter in there. So it is 2.776. Only it's going to have more decimal places after that. Right? But to 3 decimal places, it should match. There is a way that you can get these out of a TI-83. You just have to understand your calculator a little bit better. And I've done it using the solver, which is sort of like programming the calculator to do it. So if you want to learn how to do that, let me know. But you will have the T-table available too, so it's probably not worth messing with. But if you have TI-84, it's real straightforward. So okay, now we know, I have a couple more things I want to talk about this table. Notice that this number, let's look at the 95% column, it starts off with 1 degree of freedom at 12.7. That's saying I need to go 12.7 standard errors before I can be 95% confident. That's saying, well, if you got a sample size 2, so you have 1 degree of freedom, you don't have much confidence in that sample. So you're going to get really, really wide confidence interval. But it starts to come down very quickly, and even by sample size 5, it's 2.77, and it keeps getting smaller, right? Now, as it gets bigger, as the degrees of freedom gets bigger and bigger and bigger, this number gets smaller and smaller and smaller. What do you think it's going to approach? What's its limit?
0?
Nope, not 0. It's a T critical value, and we're using T because we need more variability than the normal distribution, right? But as the sample size gets bigger and bigger and bigger, the T distribution approaches the normal distribution. So what would the normal distribution, the Z critical value, be for 95% confidence? 1.96. So this thing will approach 1.96. So here we go. There's 30, and it's at 2.042. So I keep going down. Now it starts to jump by 10s, and then 20s, and then it just says, I give up. Infinity. So it goes 100 degrees of freedom, so that's a sample size of 101, and then it just says, after that, it's all pretty much the same critical value. So it just jumps to infinity, 1.96. So the bottom row of this table are your Z critical values. Yeah.
So if we have like a 73?
Good question. What if you have a 73? What I always tell people is use the one that's closest to it, but above it. So you'd use a 60. Because above it is a little too big. You don't want to use one that's a little too small. That's called being conservative. Right? So to be conservative, just use the closest one to it, but that's above it in the table. Okay? If you have a TI-84, it'll give it to you. You can put in 73 degrees freedom and it'll give it to you, but if you don't, then just use the closest one that's above. Okay? Now, back to computing this confidence interval. Oh wait, can I turn that off yet? I wanted to do that first one of the random sample. Did I write down? I never did. So I got to turn that back on real quick, and we got to look at what the summary statistics are. So, is this too distracting, or can you work with that on there? Here's the numbers that I need. My X bar is 70.4. Add and subtract the critical value, which we just looked up, is 2.776 times the standard deviation. The standard deviation is 9.529. And then what do I do with the standard deviation?
Divide by the square root of n.
Divide by the square root of n. So that's square root of 5. So do that on your calculator. And you can do it all in one big long thing. Put in 70.4 minus 2.776 times, just do it all out in one big string. And that'll give you the lower bound. Anybody got it? You should get 58.57. Got that? Now if you hit second function, enter, it'll pull up the last thing you did, and just go back to the minus sign and change it into a plus sign, and you'll get the upper bound.
Oh,
82.23, which matches what we got up there from the computer. Okay? Now one last thing to do on your calculators. I'm not going to take the time to pull it up on here. I'll just tell you what to do. Okay? Push the stat button. Go over to tests. And you'll see a long list of procedures there that you can do. Go down to T interval, which I think is the first one that's off the bottom of the screen. So scroll down to the bottom and hit one more time down. You should find T interval, because that's what we're doing. We're doing a confidence interval from a T distribution, so T interval. Okay? Press enter. Then the first thing you see is the word INPT, short for input, and it'll say data or stats. You would select data if you had put your data into a list, like into L1, you put in your 5 pulses. Then you tell it data, and then it would ask you, okay, what list is your data in? But here we just have the summary statistics, so those are stats. So highlight the word stats and press enter. And when you do that, the screen changes, and now it wants to know, okay, what's X bar, what's SX, and what's N. So enter those things. Enter 70.4 for X bar. Enter 9.529 for SX, and enter 5 for N. Set your confidence level, which is the next thing it asks. It says C level, that's for confidence. So confidence level, set that at 0.95, and then hit calculate. And you should get exactly the same interval, only it'll have more decimal places. Yeah?
Sorry, what do you do before you hit stats? You hit stats and then enter, and then you enter all that.
Yeah, so the only thing you're missing is how to get there in the first place. So you push the stat button, and then you go over to tests. And then you go down to T interval. Got it? That's it. And then it'll ask the stats or data question and all that stuff. Okay? Now the homework problems over this are going to ask you a lot of questions about is it safe to trust the results of this, that kind of thing. It's talking about checking assumptions. It will tell you that the stats or the T interval is robust to these assumptions, that it still will work often when you don't have normal distribution and your sample's too small. It's not robust to the randomness thing. So it'll ask you some questions about robust. You'll need to read that on your own. So we will see you on, what's today, Monday? We'll see you Wednesday.